So, so in this model, this is basically the model we are estimating. Yi is the infection, the cumulative number of COVID-19 infection in the city I. And Wij is the link. The link is measured by historic travels between from city J to city I. And we know that each city was linked with multiple outside cities. So this essentially will be a vector of linkage between the city I and the city city I and the city J. And the Yj is infection number, the cumulative number of infection patients from city J. And here, Ti is the infection number in the home city. So that's why we distinguish the transmission of the local city as well as the transmission from outside. So the lambda measures the spillover effect of nearby cities in the network, the transportation network affecting this city. And we here we can see that we measure two things. One is that we need to measure how the people travel from city Ji and G1 to G0, affecting the infection in the Yi. So that means we only look at the link specific change on the individual city I. And we also want to look at the equilibrium effect, which is the overall change in the change also in this link, but not only to the city of origin I, but also to all the cities combined. So that would be the equilibrium outcome. So we measure these two, and the derivation of the model the paper will be released very soon, and in the paper we derive what matters. So although it looks technical, but I just want to give you intuition about that. So here in our case, the policy targets the value of a direct transportation link between city I and city J. So through the, for example, ex-ante restriction of route-specific transportation or ex-post contact tracing on the current measures, like what Taiwan has been doing. We monitor the travelers from Wuhan and quarantine them or order tests to them or do the contact tracing to specific travelers from Wuhan city. Here on the left-hand side is the change in that direct link between two cities on the overall effect of the change in infection in the whole economy. In our case, it's China. And this is determined by three items. One is the spillover effect, how large the spillover effect can be. And the spillover effect can be estimated by the basic number of productive number, which was already offered in epidemiology studies. Or it can be based on some previous estimations of other kind of disease. And these two terms are very important. One is the centrality of the city of origin. So let's think about Wuhan. Wuhan is the epicenter at the beginning. So if Wuhan has very much a large centrality influencing nearby cities, then this effective size would be very big, influencing the overall number of infections in China. So we needed to restrict the travel from Wuhan in this case. But restricting the epicenter or the transmission origin may not be enough. We need to think about all the potential destinations. So we think about Wuhan can be linked to 100 cities. And some cities are very large cities and can have a spillover effect and affect many other cities, like Guangzhou has a direct link with Wuhan, and a lot of migrants may travel back and forth during the year, especially before the lockdown of Wuhan and before the Lunar New Year. So Guangzhou would be a very high risk destination cities because Wuhan will, so the Guangzhou will have a spillover effect to many other places in China. So we really need to be very careful about not only restricting the outbound travel from epicenter or the cities near epicenter with high risk of transmission, but also the destinations of those epicenters. So that's why we need to think about the route-specific travel restrictions.